My name is Bartosz Stojewski, and I want to present my master thesis, a relaxation algorithm in description of superconducting structures. Main purpose of this work is to find solution of Ginzburg-Landau equation in small superconducting structures that are embedded in more advanced superconducting structures. In this work, I achieved solutions of Ginzburg-Landau equations for various superconducting structures in 1 and 2 dimensions. And in case of 2-dimensional solutions, I obtained solutions for a Cartesian and cylindrical coordinate system. The IT goal of this thesis was to transfer the physical problem to the IT one. With the help of Dr. Pomorski, I started to refine the code towards possible industrial and technological uses, for example, by adding interface. This is why I designed program for GL equation solutions in 1 dimension, solver for GL equation solutions in 2 dimensions using Cartesian coordinate system, and a conversion of the set solver to C++ for parallelization purposes. Furthermore, a software for a GL equation solution in cylindrical coordinates was designed. As mentioned before, the purpose of this work is to find solutions of Ginzburg-Landau equation in small superconducting structures that are embedded in more advanced superconducting structures like RSFQ. In electronics, it is a rapid single flux quantum, a digital electronic device that uses superconducting devices, namely Josephson junctions, to process digital signals. Such device is presented on the graphics here. Over the course of my research, I use families of superconducting structures, of which some are presented on this slide. Each of the graphics represent a digital interpretation of real physical structures that consist of superconductors, non-superconducting materials, and the vacuum. On the most graphics, the dark blue represented superconductors, light blue is light blue represents vacuum, and yellow represents non-superconducting material. One of the structures depicted on the previous slide is a Josephson junction. A Josephson junction is made by sandwiching a thin layer of non-superconducting material between 2 layers of superconducting material. It is represented on the graphics on this slide. Light green is a non-superconducting material, yellow is more non-superconducting material, and dark blue are superconductors. To properly describe the next slides, I need to explain what the Ginzburg-Landau theory of superconductivity is. In physics, it is a theory that describing superconductivity, which is a phenomenon consisting in the almost complete disappearance of electrical resistance, which allows a current of a very high intensity to flow almost without losses. The magnetic field cannot penetrate the superconductor, which causes the object made of it to levitate over the magnet. The Ginzburg-Landau theory of superconductivity, like other theories of phase transitions, is phenomenological in nature, which means that it describes a phenomenon in the form of a certain equation without referring to its sources. And the general form of this equation is presented on this slide, where Fs is free energy in superconducting state, Fn is energy in a normal state, alpha and beta are phenomenological arguments, and psi is a wave complex wave function. A is a magnetic vector potential, and B is a magnetic field. If we talk about Ginzburg-Landau theory, we need to mention Schroedinger equation. It is a linear partial differential equation that governs the wave function of a quantum mechanical system. Conceptually, the Schroedinger equation is the quantum counterpart of Newton's second law in classical mechanics. It is presented on this slide for 1-dimensional case. It consists of kinetic energy part, which is the one with the minus, and the potential energy part with V, and E is total energy. Under intuitive assumption that beta goes to 0 for Ginzburg-Landau equation, we the Ginzburg-Landau equation presented here, we can see that Ginzburg-Landau equation with that assumption becomes the Schrödinger equation, and alpha plays the role of Vx minus E. The postulated fact that SCOP is a macroscopic wave function brings some analogies with Schrödinger equation that has a built-in vector potential field as well as energy of magnetic field. Furthermore, our GL free energy functional shall be able to produce equations of motion capturing the essence of London equations. Following the literature, we postulate a GL functional of the form as shown on the slide here on the top left, where magnetic field B is the rotation of a vector field A. Here we have a kinetic term of moving Cooper pairs with a momentum density squared. In analogy to the various fields of physics, we expect that our equation of motion minimize functional Fs with respect to psi xyz and the vector potential field A. What formally can be written by setting functional derivatives to 0, as shown on the right part of the slide, on the right top part of the slide here. It is useful to note that Schrödinger functional can be expressed as shown on the slide at the bottom left, where ESH stands for energy particles described by Schrödinger formalism. Vp is the effective potential in which a particle is placed. MP is the effective mass of particle, and Schrödinger wave function is psi/sh. We recognize that potential energy term is analogical to the alpha term. Hence, confining the potential Vp plays a role of alpha. This will be a basic assumption behind numerical mapping between Schrödinger formalism and Ginzburg-Landau formalism. Similarly, as before, equation of motion and probabilistic current density can be obtained by a setting shown on the bottom right of the slide. Now I want to describe a relaxation method I used over the course of simulations. In numerical mathematics, relaxation methods are iterative methods for solving system of equations, including nonlinear system. Relaxation methods are developed for solving large sparse linear system, which arose as a finite difference discretizations of differential equations. They are also used for the solutions of linear equations for linear least squares problems, and also for systems of linear inequalities, such as those arising in linear programming. The graphics presented on this slide is a diagram that shows how I use the relaxation method. I'll describe those in detail on the next slides. Yes, so first we compute d over dx cx from TE, which is our wave function. The d over dx ax, which is our vector potential field, a gradient of second derivative of psi and second derivative of vector potential for every point in space. Then we compute electrical current for every point in space. The the next step is computing changes of magnetic vector potential field and psi for every point in space by using equations shown below. Then we apply our calculated changes in SCOP and vector potential for every geometrical point in space, as shown on the equations below. Then we check boundary conditions and correct certain physical constraints. Next, we check the values of numerical error array error relative to psi and the total relative value of error TR relative psi in the current stage of numerical solutions of Ginzburg-Landau equation. Then we compare the values, the calculated values with previous values of those errors. Then we increase simulation time from TI to TI plus 1. Otherwise, we stop the simulation, or we tend to stop if phenomena of error increase and continues for many new iterations. Next step is checking the value of free Helmholtz Ginzburg-Landau energy at time Ti plus 1. If the value of free energy at time Ti plus 1 is smaller than the value of Helmholtz free energy at time Ti, we increase iterative time by 1. Then we compute a derivative of TR relative psi with respect to iterative time, as shown on the equation here. Then we compute the derivative of free energy with respect to iterative time, as shown below. Next, we implement auxiliary error function RAUX that monitors processes of GL error and free energy minimization at the same time. It is expressed in the equation here. Then we compute this function this function derivative with respect to iterative time. And lastly, very sporadic or very rare or only one time, we add some Gaussian noise of very small amplitude to SCOP in order to tune SCOP distribution as accordance to aligning algorithm methodology. Execution of steps 10 to 14 in GL relaxation method is not compulsory, but still allows for a good insight into progress of obtaining proper SCOP distribution as a result of minimization of Ginzburg-Landau free energy and Ginzburg-Landau numerical error at the same time. And here there is a Ginzburg-Landau equation solver in 2 dimensions presented. We can see that it can load various initial alpha distribution field. It can we can change various simulation settings. Implement various mathematical expressions that will be our initial SCOP guess function, and activate various settings described in more detailed way in my work. The IT goal was to develop the method and effectively implement this method by parallelizing and constructing the interface. The interface speeds up the use, get the results faster and more conveniently. On this slide, we can see how the initial SCOP progresses over the time of our simulation. On the left, the static image on the left presents our initial distribution of SCOP, which in this case is our 4 Gaussian peaks. On the right, there is an initial distribution of alpha, which corresponds to a system of superconducting squares placed in a vacuum. And in the middle, there is an animation that presents how SCOP changes with each time of the iteration, which in every 100 iterations. Next, I'd like to present what was achieved in this work. First obtained thing is a new one-dimensional Ginzburg-Landau solutions and the ability of this method to describe Josephson junctions in the case of a curved superconducting wire in the quasi-one-dimensional approach. Resistance of the obtained numerical solutions this shows resistance of the obtained numerical solutions of a Ginzburg-Landau equation to any trial function of the superconducting order parameter. These results, the results perfectly confirm the literature results for the so-called intuitive SCOP trial function in line with physical intuition. Next is the formulation of the mapping of the Ginzburg-Landau equation in solutions of the Schroedinger equation in 1 and 2 dimensions and with the Cartesian and cylindrical coordinate system. The trial function of the superconducting order parameter is very neatly used here, obtained as analytical solutions of the Ginzburg-Landau of the Schroedinger equation for the ground state. Next is the formulation of criteria for automatic shutdown of the simulation. This criteria is of great importance in the case of superconducting integrated structures, and it was initially numerically tested. Then is a superconducting parameter, a distribution for unconventional Josephson junction matrix. The superconducting parameter decomposition for the unconventional Josephson junction matrix and significant acceleration was observed in the transition from sequential to parallel code execution using OpenMP libraries. Next is the methodology of simulating superconducting structures with a variable geometry during the simulation as it is presented on the slide, which is of great importance in the description of superconducting complex structures, starting from the solutions obtained for simple superconducting structures. Next is a creation of a solver in a Matlab for two-dimensional structures in Cartesian geometry using the Ginzburg-Landau relaxation method. The solver allows to enter an SCOP analytically by using a formula or to get an initial SCOP from a file. But what is more, we also have the ability to numerically map analytical solutions of the Schroedinger equation to SCOP as a very good trial function. Then next is introducing elements of the annealing algorithm during the simulation, of a GL relaxation method, which is visible in the presence of the characteristic noise while minimizing the free energy or the numerical error. The incorporation of the annealing method into the GL simulation increases the accuracy of the numerical results and contributes to the development of the GL relaxation algorithm. Next is a simulation a grid of superconducting squares under a 90-degree rotational symmetry and protect this symmetry from possible numerical instabilities. Simulations were performed for the entire class of superconducting structures in contact with a vacuum or non-superconducting material using the mapping of this geometry to the field alpha in the GL formalism. Satisfactory solutions were obtained for superconducting structures in the simulations in the situation the occurrence of a vector potential in the direction with or without that potential. The Meissner effect has been indirectly proven. Next, how to solve a Ginzburg-Landau equation. In 2 dimensions, it's hard to solve this equation analytically. For that, we need computers and proper algorithms to solve GL equations. However, various analytic solutions of one-dimensional Ginzburg-Landau equations can be confirmed by usage of a Mathematica software in a symbolic or in numeric mode. In the equation, and it is presented on the slide here. In the equations presented, elliptic f is the elliptic integral of the first kind. On this slide, we can see the GL relaxation method simulation for one-dimensional case described by the equation here at the top. Each of the results presents simulation results for intuitive and counterintuitive gas functions, as it is described on the plots, with initial being intuitive function and initial 2 being counterintuitive function. For 2 dimensions, the GL equation will have 2 forms, depending on if we use Cartesian or cylindrical coordinate system, and those equations are presented on the slide right here. Then we proceed to the GL relaxation method simulation examples. First is a Josephson junction with initial distribution of SCOP being a large single peak covering all grid, and this is the obtained result. Next, this example is simulated without the presence of vector potential. The vector potential, however, is introduced in this case. It is shown on the graphics, on the top right graphics, and the result is on the left graphics. Then we proceed to another example, which is such superconducting structure with a large superconductor and 3 non-superconducting elements in the vacuum. And as just as before, we first perform the simulation for without presence of vector potential, as shown here. And next, we added the vector potential as presented on the result here. Next is the same structure as before, but this time we use an initial distribution of SCOP as 2 Gaussian peaks instead 1 large peak. And the results are presented on the slide right here. Similarly goes with the initial distribution of similarly goes with the vector potential as shown here. It is worth to mention that previously we had a symmetrical vector potential, but this time is not symmetrical vector potential. Next, we have another structure with which is a rectangular superconductor with 4 rectangular non-superconducting materials attached to it, and results present as follows: without the presence of vector potential and with the presence of a symmetrical vector potential. Next, I'd like to talk about why I use the parallel programming, and I use it because we write the code with specialized software to make it easy for them to run their program across multiple nodes or processors. A simple example of where parallel programming could be used to speed up processing is our for loops, as shown right here. On the right side, there is it is a sequential for loop in my program, and on the left there is a parallelized for parallelized for loop in my C++ program, and I use it to reduce simulation time. I did it with the usage of OpenMP library, which is it's important that in OpenMP we have real and virtual threads. We will distinguish between the real threads and the virtual threads. The real threads are available cores of our processors, while virtual threads are threads that are manually created by the program for its needs. For multi-core processors, the optimal situation is that each and every virtual thread is served by one core. And here is the output of a Matlab sequential program presented on the left, and an output of a C++ parallelized program on the right. On the bottom, we have estimated simulation time. We can see that parallelized program is run by parallel. You can see that by parallelization of the program, we achieved results much faster. We achieved our results much faster. Here we can see the plots of average error and average free energy for a sequential program. On most left, in the middle there is average error and average free energy for a program, for a parallelized program. And on the right, it's an error. It's a plot of average error multiplied by free energy, and we can see that all those plots are minimizing, which is what we were trying to achieve. The methodology used to achieve results presented over the course of this work can be further improved, for example, by usage of curved cables. The topic description of coupled field inducted Josephson junctions in curved Ginzburg-Landau equation was already accepted for International Conference on Quantum Materials and Technologies in Turkey. On the right, there is a teaser for that conference, which is a curvature modified Ginzburg-Landau equation. In this equation, S is the distance between from the beginning to the end of the loop. To finish this presentation, I want to present lengthy calculations to get the following GL equations for SCOPs and magnetization and the Ginzburg-Landau free energy achieved by Kazuhiro Kuboki and Keiji Yama. I present those equations because the proper implementation of a relaxation method could solve those equations, because relaxation method might not be the most precise one, but it is very stable and capable of solving such bulks of equations. Thank you for your attention.